Hello. So we're going to talk about the calculation side of the bomb calorimetry lab that you all are going to start off doing. So the main question that we have is 1-butanol, 2-butanol, and cyclopropyl methanol. So 1, 2, 3. So there's a cyclopropyl, and then you've got methanol here. And so if you look closely, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, all the same number of carbons and one hydroxyl group, but slightly few different number of hydrogens. But the energetics associated with creating this tricarbon ring, triclic ring? No, whatever it would be called. 3-membered ring, there we go. The energetics associated with this compared to these two is going to be a way that we're going to study what's called ring strain. And so your colleagues who are doing bomb calorimetry at the moment, they are determining the delta H of combustion of these 3 compounds. But delta H of combustion, if you think about what a combustion reaction is, so you've got your, let's say it's a butanol, plus O2 yields CO2 plus H2O, right? And if we think about a Hess's law diagram, so there's going to be some delta H of reaction here. And since this is the combustion reaction, the delta H of reaction is going to be the delta H of combustion. If we think about the Hess's law diagram to where you have your reactants, so this would be butanol and then O2, and then think about, first of all, what is this type of reaction, endothermic or exothermic? Hopefully you said exothermic, which means delta H of reaction, positive or negative, should be less than 0, which means in comparison to the energy of the reactants, the products should be located right down. So you got your products. And this is your delta H of reaction. But we all know it takes energy to break bonds. So the way that you would represent this schematically is to say, okay, so here's the delta H associated with breaking all of these bonds. Here's the delta H of forming. And then you take the difference between those two. So products, the delta H of formation of the products minus the summation of the delta H of formation of the reactants. Okay, and so since we're looking at the difference of those two, that difference gives us this delta H of reaction. Go team. Okay, and I should also mention that this is multiplied by the number of moles that are present. Okay, so what we're going to do is we are going to use what are called ab initio calculations to determine the delta H of formation of each of these using various types of quantum mechanical methods. And then we're going to utilize Hess's law to figure out what the delta H of combustion would be from a completely first principles, no experimental data, only from quantum mechanical principles are we going to figure out these numbers. Then next week, you're going to go into the laboratory and you're going to find out what they are experimentally. Your colleagues, however, are starting experimentally, and then they're going to come in and see what it should be theoretically. And then you're going to have a great comparison to do. Cool? Okay, slight difference though. Notice I didn't write the what it's broken up into up here. If you're doing calorimetry, the idea is that it's broken up into an oxygen atom with its electrons, carbon atoms with its electrons, hydrogen atoms, and so on. What we're determining are the electronic energies, different than the enthalpies. The electronic energies are the energy associated with bringing in all of the electrons and the nuclei. So if you count up every nucleus, so you have however many, 1, 2, 3, 4, so 4 carbon nuclei, and each carbon has 6 electrons. Is that right? Yeah. So that would be plus 24 electrons just from the carbon, plus however many hydrogen nuclei there are, plus however many electrons hydrogen has, plus the oxygen, plus the 16 electrons that the oxygen brings. Cool. So it's not like you're looking at the nuclei and the electrons as still a bulk together. They are actually completely separate from the quantum mechanical perspective. So we're going to have some corrections to make. Go team. Okay, so that's the idea of the lab. And in doing the calculations, you're going to be able to find dipole moments, so dipoles, bond lengths, which I'm guessing the links here are going to be slightly different than the links here. Remember, you're going to be writing a communication and a full article on this whole topic. So good to take some extra data. What else can you do? Oh, coordination or conformation. So this is going to have two different types of conformations. This is going to have probably an interesting conformation. So a lot of things to explore. Y'all wanted to have a true research-like experience? Well, this is what it is. There is no lab handout for this. I have a couple of papers that are going to be helpful, and I have a website that's going to help you kind of guide you through some of the calculations. But other than that, you're on your own. Investigate ring strain. See what you can find. And I would hope in that you're going to hypothesize that one of these is going to have, like, that this might have a higher and or lower energy associated with these two, or compared to these two. Okay, cool. So that's the overall essence of the lab. The next video is going to talk about ab initio calculations very, very briefly.